Random sample consensus for previous called Ransec. Before we start, these slides are available over podcast. You should be able to find out the podcast link. So the way it works is if you are concerned about your bandwidth usage, please stop this video. Go back to the instruction. You should be able to find the link where you can download the PowerPoint slides along with a link to an audio track or a podcast which has the minimum number of bytes required, and then you'll be able to follow the instructions because we'll be saying next and pointing out a few slides along the way. So welcome to computer vision random sample consensus. And it's obvious when you talk about consenting or consensus or agreement, we talk about samples and we get from these samples random selections. Let's move next. You should be able to find to the right hand side slide number which we'll be using it. So we'll move next to the copyright.
This video is subject to copyright.
So this video is subject to copyright.
To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
Welcome back. So the reading associated with this particular presentation will be the book chapter 6 section 1. I will move next to the next slide. We talk about outliers. Usually in any population of numbers or features or corners, we have, as what you see here in green to the right hand side, called the inliners, which basically is a set of members or elements which comply with the specifics. And then you have the outliers, which basically is the extreme. On some other context, we talk about this as the boundary conditions. Sometimes we talk about it as odd members. So in this particular features here, the red ones is the outliers because they don't exist into the common chain or the common members location. So if I want to talk about the image we see here, to the left hand side you have the comic book, and to the right hand side you have the layout of the top of a table where we have this comic book, and then the points or the corners which we see in the green bubble, it basically showed all the members. However, there is a corner which matches some corners on the cover which actually do not exist to the cover. So if I wanna ask about how robust these corners are or how exactly these corners are, so I will talk first about a very simple example, which basically the linear regression. So in a linear regression, we want to take all the location of the corners, and then we would like to fit these corners with a line. So to fit this corner with line, we see here on front of us on the right hand side, you have the dots or the corner location, and then I would like to approximate these corners into a line. So for example, I can do the least square fit, which basically I will find the line where there is the least square error of all these points. The fitting problem, we talk about how we can fix this problem or how we can find this line. So any suggestions? It's basically what we need to find out is a better cost function to find an approximation or to find a similarity between these points. So if I move next to the slide called idea, so I would like to get a hypothesis line, or I would like to propose a hypothesis which would lead to a line, and then I can count the points which agree with this line or comply with the line. We call them inliers, and for the ones which is outside the compliance criteria, it will be called outlier. So for all possible lines, I can select the one with the largest number. So let's move to the next slide where we want to count the inliers. So for example, if I have the hypothesis of drawing a line, as if you see here in front of you the red line, the question will be is how many points comply with this line. So basically we have 3 points. So the inliers here are 3 points. If we have another suggestions of having the green line and then count how many in line with this, I will find that the inliers here are basically 20 lines. So the question will be is how do we find the best line? So unlike least square error, we don't have a simple answer. So there is no simple solution. So basically what we can do is we can look at hypothesis, and this hypothesis you can call it in a different way as a try and error. So we can be giving a number of images. Inside this image I will get multiple lines, and then I will try to find out which lines will give me the best match. So here I'm looking for a translation. So I would like to see the number of points which moved between left to right. So I will pick up different corners and I will try to figure out the matches of different corners, and this will give me more matches, and at the end I will select one match as a random and I will call it inlier, and from that point I will try to derive a pattern, or I will like to derive a number of a line where these inliers will accumulate, and then I will figure out if this match, and you have a criteria. Then I can select a second match at random, and then I can look at which inlier will match this second one, and I can keep going. And the idea here can be simplified in what we call it the random selection, which basically the idea is all the inlier will agree with each other on the translation vector, and we look at the smallest possible number of outliers that disagree outside the translation vector. So we speak about Ransec has only a guaranteed if there are less than 50% of the matches are outside the trend. All good matches are alike, and every bad match is a bad in its own way. So the inlier threshold will be usually related usually to the amount of noise I can accept. So if we model this as a Gaussian, we can always look at a standard deviation of 3 corners. We can look at number of rounds. We can look at percentage of outliers. We can suppose usually there's an unusual rule called 80-20, where basically we have an 80% of the points will comply, and 20 will be the outliers. So we can look at different rounds. So here I have on this slide X translation and Y translation, and I will be looking for the corners which will give me the movement, and then the threshold here is 95% of Gaussian lies inside that radius. So this is the linear feature which will move. So back to linear regression, I will have these are the distribution of different corners. I will generate a hypothesis, and the hypothesis can be that I will split these numbers of pixels or corners or features based on the line which will pass through to minimize the error. So this accumulation here will represent the inlier, while the one over the top of the Y represents the outliers. So in a general version, we choose set samples or different corners randomly, and then we look at these samples if they fit a model. Once they fit a model to these samples, I will count the number of the inliers that will fit this particular model. I will repeat this n times because I have basically n pixels, so I will, or n feature or n corner, I will try to each one, and then I will choose from my models which one will have the maximum set of inliers. The questions will be is how many rounds can I go? if we have to choose S sample each time, which is the inliers have the ratio E, and we want to have the right answer, so the probability will be n less than or equal minus log 1 minus b over log 1 minus the group of 1 minus e to the power s, and this will give me the number of rounds which I will go. And as you may want to see that whenever we increase the number of rounds, it will be increasing, or whenever the probability will be more distributed, will increase the number of rounds. Now the question is how big S could be as a sample. So we understand from before that we have specific operations. We have 6 different operations which will occur on any corners or any relation between pixels. So we can look at this particular relation, which basically translation or rotation or shear, and from that point we can look at the changes, and then we can get. So the random selections consensus we'll look at the pros. It's a simple approach and general. You can apply it to so many problems. You can often work well in practice. However, the parameters need to be tuned and sometimes need to be personally tuned. Sometimes too many iterations is required, and it can fall into extreme low inlier ratio, and it can often be a better than brute force. So a brute force sample like it's always a comparison. How like can you do a brute force like first and then you keep going, or you can select random? Maybe you can have a better approach. And the final step, if I find the average translation vectors over all the inliers, so if I have some of these inliers are belong here, so the idea here is I have these features or these corners on the right hand, and then on the left hand, and then I will look at the matching on the right hand. If I find as many as I find the average transition inliers, and then this will give me the least square. So Ransec is an example of a voting mechanism where I will have each hypothesis will get each data, and then best hypothesis will win. There are many other types of voting schemes like Hoff transform, which will be covered more inside the tutorials. And if we want to create a panoramic view, we will be giving 2 images, and then I will detect features, I will match features, I will compute a homograph using Ransec, then I will combine the images together, and what I will have will be more than the 2 images. So here there is an example of how we can build a 360 panoramic view. The blue rectangles and the red rectangles are different images, and all what I will do is I will collect different corners, and then I will be able to match them using the Ransec. And if I want to use this panoramic models, I will show you in the next lecture how we can use, and why, if we want to figure out this, why will help if we get to understand the camera. So the 360 panoramic view, you can see it here, has been built by matching images and the corners in this way. And if you have any questions, please send me an email to my email, or write the notes in the comment below. I understand this might be a very simple concept. You may look at it as a very hard concept. However, it's a very simple concept. It's an optimization or an idea of someone, and you may want to go back to the video and watch it again. You should refer to the book for more reading on it, and it's basically a concept where I would like to see I will have 2 images. I want to match corners between 2 images, so I put the hypothesis by looking at similarity between the distribution of the points, and I will pick up random samples and try to figure out the best match, and then I will try to find out the correlated points, which will create a line, and these correlated points will give me the line where the most inliers are in and the outliers are very small. Looking forward to hear your feedback, and have a nice day. Thank you.